right, folks. Welcome back, everybody. We are going to be continuing with our notes today. We finished with stars. We finished with the sun. The next thing we're going to be doing is we are going to check out some other stars more specifically and see what we can find out about them as their gas, as their nuclear fusion that keeps them running starts to run out. And so, what do we have right here? Nope. It is kind of a circle. This is a black hole. And so what we're going to be doing right now, listen up guys, what we're going to be doing right now is we're going to take the USS Hathaway and we are going to jump right in to the black hole and see exactly what happens. Go ahead and write down stellar remnants. These are your notes today. So, what's a remnant? The remains of something. And what does stellar mean? Stars, yeah. So this is going to be what remains after stars die. We're going to see what goes on here. So the first star that we're going to talk about, of course, is going to be the sun. The sun is a relatively average-sized star if you would average out all the stars that we see in space. And we're going to walk through exactly what happens when the sun starts to run out of fuel. So the sun is powered by nuclear fusion in its core, and we talked about this when we looked into the sun specifically. It converts hydrogen into helium. There's enough high temperatures and there's enough pressure in the core of the sun that the hydrogen that's in there actually gets squeezed together, and that creates helium. And that process sets off a nuclear reaction, and that's where that nuclear fusion comes from. That's the energy source of the sun. That's why it is pushed out to that size. So the question is, what happens when the sun runs out of hydrogen? Write down death of a low-mass star. And then put a dash and then write down the sun. That's something we can talk about in terms of how would life on Earth change. I think someone asked that not long ago, and I think we said you'd be able to live for a month or two because our atmosphere is strong enough that it would keep temperatures at a reasonable level for a while, but eventually the oceans would freeze and all the water would freeze and crops would be bad and we'd all die. But it wouldn't be instantaneous. If the sun flipped off like a light switch, we would not instantly freeze to death. It would take a while. We should be okay. No, we'd be fine. So, a little bit about the sun as it's running out of fuel here. We're going to get more specific into this. So I'll let you know what to write down in just a second, but you can kind of just follow the timeline here, because the sun only has a certain amount of hydrogen. So eventually, all that hydrogen, which it's fusing together to create helium, that's eventually going to run out. And so what ends up happening is after 90% of the hydrogen is gone, then the core shrinks and gets hotter. And the reason it's going to shrink then is because that process, that nuclear fusion, those nuclear reactions that are taking place, those are providing the sun with all the energy that it's shooting out in every direction. And that energy is what gives the sun its shape. If you take away the source of that energy, then there's nothing to keep the core from crushing down. And that's essentially what we start to see when 90% of that hydrogen is gone. The remaining hydrogen burns faster because now the core has shrunk more and there's more pressure and it's fusing it faster. And so it's creating some extra energy. And that extra energy causes the sun's outer layers to expand into space. Any guesses on what we would call the sun once it reaches this stage? Nope. Good guess. Yeah, red giant, exactly. So as the sun's layers expand, because now it's got a lot more energy pushing out, you have the sun turning into a red giant. And those layers cool as they get further out, and that's why they look red. For this one, just go ahead and write down, let's see. Let's go back here. Write down this first bullet point. And then the last bullet point here. Better turn the fan on. Otherwise we might overheat. There we go. That could have been close. Yep, first and last bullet point. So yeah, as the sun's core shrinks, that extra pressure is going to allow the hydrogen that's left to burn faster, and that extra energy causes the sun to expand further into space, and as its layers get further out there, they cool, and they then turn red. From this one, go ahead and write down outer layers cool, and then change outer layers cool, and then the second bullet point. So just these first three letters, first three words, and then the last bullet point there. So as mentioned, the sun turns into a red giant. So obviously it's bigger than it used to be. So the question might be, how much bigger does the sun get? So let's say this is the size of the sun right now. Any thoughts on how big this might get when it turns into a red giant compared to this picture? So like maybe just, I'll kind of start my finger right here. And when it gets to the point where you think that's where the edge of the red giant would be, just let me know. Okay, I heard one guess right here. Yeah. Okay. So we've got kind of three guesses on how big a red giant sun would be. Ugh. Yeah, I've drawn worse. So let's see how much larger the red giant's actually going to be. And there you go. So probably a little bit bigger than this dotted line here. You can see the sun at its normal size there, and this would be red giant sun. Now the red giant sun is big enough that it's going to cause some actual direct damage to some of the planets in the solar system. Go ahead and write down the sun's new size swallows up Mercury and Venus. Yeah, I mean, this is kind of an artist rendition of what the Earth might look like. We don't really know exactly what it would look like right before we're fried to a crisp. But this is, I suppose, as good a guess as any. You can see Mercury right here getting pelted. You can see Venus right there not doing much better. So, yeah, Earth just barely escapes being swallowed up. We're just outside the zone that the sun's surface would be. But it would look like a massive thing if you actually can see the sun as it rises and as it sets. Our atmosphere, though, would burn off, everything would be fried to a crisp, and no life could survive. So even though we don't get swallowed completely, you're not going to be around to see it. So just a couple pictures on what that might look like here. This might be the horizon as the sun is rising there. And then as it's setting, because again, remember, the atmosphere is going to get burnt off. So you're not going to see any, beautiful red or orange clouds or anything like that. You would just see the sky. You would see outer space there. Now, this isn't the end of the sun's life either. From this slide, go ahead and write down the first bullet point. Then that third bullet point and the fourth up until pulsate. You don't need the last bit. Well, the first one, the third one, and then the first part of this last one there. So, yeah, as the hydrogen that's left is used up, of course, now there's not as much energy pushing things outward anymore. And so the core shrinks again, and it gets even hotter. And eventually you get to a point where there's actually enough pressure and temperature in the core of the sun that not only can the sun fuse hydrogen atoms together, it can fuse helium together. And when you fuse a higher element like that, you give off much more energy. So when you're fusing helium atoms together to create carbon, that makes the sun put out even more energy than it originally was at the beginning or when it was turning into a red giant. So that helium fusion causes the sun to pulsate, and it turns into a yellow giant. And again, the reason it's a yellow giant now is because now that it's fusing helium, it's putting out more energy and is even hotter. When it was a red giant, it had cooled off a little bit because its outer layers had expanded into space and cooled down. But now that it's much more energetic, it's giving off more energy from that more powerful fusion, the sun turns to a hotter yellow as opposed to the cooler red.
How long would this all take? Just like 10 minutes?
No, I mean, this would take a long, long time. Thousands or tens of thousands of years, hundreds of thousands maybe. It's the sort of thing that we don't have to worry about happening, and it's the sort of thing that if it started happening, we wouldn't see the end of it. No. The sun is very stable. It is not nearing this happening anytime soon. Some more artistic pictures there. Now, again, we're kind of following the same process. What happens when all that helium starts to run out? Well, once the helium is 90% gone, then the sun turns again into a red giant. But now, because it's as a result of this helium, it's going to be even bigger than before. And now it actually does swallow up the Earth this time. And when it reaches this point, the sun is it would be nearing the end of its lifetime. That hydrostatic equilibrium that we mentioned before, how you've got, all the mass of the sun, there's a lot of material there, and it provides that gravity that pulls the sun down, but at the same time you've got the nuclear reactions happening in the sun's core that push everything out, and that's why we have that equalizing pressure there, because those two forces are opposing each other. Well, now, once you get to this point, hydrostatic equilibrium is just gone forever. The sun has much more energy pushing outward than inward, and all those layers expand out into space, and you're left with something that's called a nebula, which is basically the remnants of what our sun would turn into. And finally, actually, go ahead and... Now you can skip this one. But yeah, a nebula is when a star has burned long enough and hot enough that its layers have just expanded out and are no longer part of what you would call the actual star. It's basically the remnants that look like clouds from the layers that used to be that corresponding star. And this is an example of a nebula right here. Nebulas are not violent. It's just those cloud layers moving further and further outward, because that's what happens when gases are no longer pulled in by an active force. They just expand. And actually, in this one right here, you can see this is what's left of that star. And these are the remnants of its outer layers that are expanding into space. It does. And this doesn't take long. It doesn't take long to go from this to something that isn't quite as spectacular. This effect dims very, very fast. Another neat nebula right there. And now to the very end of what would happen to the sun. Go ahead and write down the first bullet point. The first one yeah, I can't really shorten this. Write down the whole thing. Yep. Take your time.
Are we just learning about depth of low mass stars, or are we doing high mass stars?
Nope, we're moving on from here. We're going to learn about, so this was low mass stars, or average mass stars. After this, we talk about very high mass stars, and after that, extremely high mass stars.
All day.
Nope. This is going to expand into tomorrow.
Just 2 day notes.
2-day notes. This is only the. I think we've only got 3 things we're taking notes on, including this now.
Really?
Yep.
That's 2 hours.
Yep.
Yeah.
Yes.
It's the worksheets, right?
It's on your handouts. Yep.
The handouts.
As long as you meet all the criteria.
I
Yep.
honestly forgot about that.
Speaking of handouts, I actually have one for you here.
Shoot, does that mean how much like the church is?
Is that Mr. Joe?
No, it's December. Shoot, then I might not have to take in. Oh, I might have taken the Spanish one. He's not here. Well, I want him to say learning not for much. And then there's stuff like that.
This? Oh, there's more after this. We'll be going until the bell.
How about
A girl, anyway. Right here. This is literally my own.
All right. So the next slide you're going to have to write down too. Yeah, this whole thing.
You're making it great.
I don't know. I mean, what I probably did. They make no sense. Well, what I probably did is I took the scientific definition and I shortened it as much as I could. So.
oh, shoot, right?
So I do want to try and connect this all together. So I'm going to quick go back to the last slide, and I'll come back to this one. So like I mentioned, eventually the core is going to run out of helium to fuse. And so when that happens, the core, even though it can shrink yet, it does not have enough pressure and heat to start fusing that carbon together. Because carbon, again, is what happens when you fuse helium together. So if there's not enough energy to fuse carbon together, all you're going to be left with is just a shell of what that core used to be. It's white hot, it's all carbon, and it just sits there, and that's what we would call a white dwarf. Eventually, over time, it would decrease in temperature and cool down, and then it would become a black dwarf. And this is the sort of thing that would physically happen to all stars that are our sun size or up to 10 times bigger than our sun. That's what would happen to those stars. Now, this isn't necessarily the end if that star would get to that point, because what can happen is if you have another star or object get close enough to the remnants of that core, that object, that core, still has a lot of gravity. There's a lot of material there, and it's very dense. So if something gets too close, it can actually pull that material off of that star and try and almost suck it up like that. So what ends up happening is you get these explosions from the material that's then pulled from those stars. It's kind of like a parasitic thing, actually. So then it fuses into helium, and it fuses explosively into helium, and those nova explosions do not destroy the star. They're not big enough, they're not bad enough to do that. However, there is a type of explosion that can destroy what's left of this tiny little star. I feel kind of bad. We've taken these stars and we've basically killed them, and now we're going to see what happens to actually destroy and blow apart what's left of the core. That can happen if you have enough gas or material collected. Then you have something known as anybody know what it is? Supernova. Not a nova, but a supernova. And from this slide, I'd like you to write down what you know. Okay, write down the first bullet point. And then just write down this. Blows that white dwarf apart. Yeah, write the title too. This is a type 1 supernova.
Do you write the dashes also from the first?
No, just the first bullet point and then what's underlined. So again, what happens now is if you do have enough material and then you have enough pressure to then fuse carbon together, you're going to get oxygen. And if you have enough of that, you're going to create silicon. And then if you have enough silicon to fuse together, that would create nickel. And if you have enough nickel for nuclear fusion to take place, that nickel is going to explode. And it's going to explode very, very violently. Violently enough that the remnants of that white dwarf are going to be blown to smithereens. The nickel is going to expand into space. It would eventually decay into cobalt, which would decay into iron. And that would be the end of the story for that low-mass star. Questions on what happens to these poor little low-mass stars? And again, this would take a long, long period of time. If we observed a star beginning to die right now, chances are Judgment Day would happen way before it would go through these stages. These would take a long time physically for these processes to unravel. But and we've never seen this occur. We've seen the actual explosions, but we've never seen a star actually go through these stages. So this isn't something that we've actually used observable science to look at. It's just physically, when you look at the molecules and the chemicals and everything involved along with the gravity and the forces, this is what should happen as these stars run out of fuel. And this is kind of summarized on your handout on one of the things. You can look at this at some point. As promised, now we're going to see what happens when a big, big star goes through these same phases. Write down death of a high-mass star. So now we're looking at stars that are greater than 10 times the size or mass of our sun. And we're only going to a certain point. If you get to the supermassive stars, like some of the biggest out there that we've talked about when we looked at those stars, something different happens with them. But we're going to talk about the real big ones. And there are plenty of these you can see at nighttime. If you can find Orion in the winter, which is pretty easy to spot, his, I don't remember if it's his right or his left hand, but it's a real big blue star, and that's Rigel. And that's the example that we're going to be looking at here. Write down death of Rigel. Well, never mind. It's actually his, if you're looking at him, it would be his bottom right leg. His bottom right foot would be Rigel. Big blue star. So, all you have to do for this slide, again, is just write down death of Rigel, because this is all very similar to what would happen to our sun. It burns through its hydrogen much faster than low-mass stars, and the reason for that is because it is a high-mass star. If it's got a lot of mass, and it's got a lot of pressure then, it's just going to burn through that fuel much faster than a low-mass star would. It's like having a car that doesn't get as many miles per gallon. You're burning that fuel at a much faster rate, probably because it's a bigger car. As it runs out of hydrogen, the star grows, becomes cooler, just like with low-mass stars, and it turns into a pulsating yellow giant first. And again, the reason for that is because it's big enough and massive enough that it's burning that fuel at a much faster rate, that it doesn't go straight to a red giant. Remember, red giants happen because you're starting to burn that fuel, but it burns it fast enough that those outer layers expand far away from the star into space. Here, that big yellow giant is going to keep its shape, more or less, and keep its heat. So, here's what happens. You don't have to write any of this down. But when it's done with its big yellow pulsating giant phase, then it turns into a massive red giant, because eventually it will get to the point where its layers will expand away from the star itself. The core is compressed, and it gets even hotter, much hotter than a low-mass star's core. And so then we kind of go through this same procedure. So it begins to just fuse the helium together, and that creates carbon. And again, this is where our story ended for stars the size of our sun to 10 times bigger. Unless you have something that it's, parasiting off of, pulling more material from, this is the end of the story for things like our sun. But if you have something big like Rigel, now you can actually, from the get-go, fuse oxygen to create silicon, and fuse silicon to create iron, and fuse iron. But if you get to iron, when iron fuses, it actually releases no energy. It's kind of a strange characteristic of iron. And so what ends up happening here is, go back quick. So when iron fuses, it creates no energy. And then what ends up happening is because that fusion does not release energy, now, just like before, that hydrostatic equilibrium is completely gone. Just like before, when you don't have that outward pressure anymore, now you've just got that pressure that's sucking everything in, that gravity. Now there's no energy being released from that iron fusion, so there's nothing pushing out. You've only got forces pulling in. And if you've got all this material, because we've got a star that's way more massive than the sun, that collapse is going to be completely catastrophic. And it creates something known as a type 2 supernova. Write down type 2 supernova. And then just write down the first line of this next bullet point. The core collapses in less than a second. Is there?
Yeah, he wears a bucket, basically.
He sounds like a popular one. Is he DC or Marvel?
Marvel.
Okay.
Yeah. We also have Nova Course.
Oh, okay. So then the question is, what happens to this star as its core collapses? And that's where we're going to pick this up tomorrow.
Big.